on here. Some students were asking about attendance. Attendance does count for 5% of your grade. I'm going to take attendance on arbitrarily selected days, okay? So probably maybe 5 times during the quarter. Usually at the end of class, I'll pass around a piece of paper and just have you sign in, okay? And so, so you have to be here, even if you have a good excuse for not being in class on that day. If you're not here to write your name down on the piece of paper, you're not going to get an attendance point, okay? So, you know, even if you have a very legitimate reason for not being in class, you have to have your name on that paper to get credit. Even if you come for the first half of class, if you've left early and I pass the paper around at the end of class and you're not around for it, you're not going to get your point there, okay? So, and that also means, you know, if you show up 10 minutes before the end of class, but you happen to sign the paper, then you'll get your point, okay? So it's not super strict, and, you know, you could come to every class but just happen to miss the arbitrary day that I passed the paper around. That's just how the attendance thing works, okay? I think that's it. Yeah, again, if you have issues with anything, contact Sue Kwan regarding administrative issues. So she's the one to see there. Okay. Are there any other questions about the course before we get going here again? Oh, another student asked about extra credit. I don't have extra credit. I don't believe in extra credit because but I haven't needed extra credit in the past. I think I'm very fair in my grading. I think I'm very fair in the resources I provide for you to succeed in class. So I haven't needed to have extra credit. There is an opportunity to get over 100% on the midterm and final exam if you answer all of those questions. Some of those questions are bonus questions, and so you can get over 100%. But I haven't needed extra credit. Inevitably, some students will not pass the class, and they will send me emails about what things they can do to pass. But I have to say, you know, what do you need to do to pass the class is a question that you need to be asking yourself now, and not at the end of week 12 after you've taken the final exam, okay? And so what do you need to do to pass? I would say study for each week's quiz. Every week I'm going to have information up on the website about what you need to know for the quiz. Do your homework. Make sure you understand the concepts covered in each homework. And that should prepare you well to do well in the course. Don't send me panicked emails after the course is over saying, well, what do I need to do to pass? Because the answer is, here's your answer, but you needed to do it 10 weeks ago. So, okay, we'll move on here regarding data. When we'll talk about gathering data. Okay, data can come from observational studies, or controlled experiments. Okay. There's also What does not count as statistical data are anecdotes. Okay, anecdotes or anecdotal data. Okay, and so, I guess one thing I want you guys to walk away with at the end of the course is that data coming from observational studies or controlled experiments, if the studies or experiments have been done correctly, this data is much more reliable than anecdotal data, okay? So data from a properly conducted study or experiment is trustworthy, okay, and we can trust that data much more than anecdotes. Okay, what I mean by anecdotes is, someone tells you, oh, my grandmother had cancer and she did this thing and it healed her cancer, okay? And we're not discrediting these things that happen in anecdotes, but one story or even a handful of stories is not enough to say this treatment or this course of action or this is an effective way for fighting cancer or fighting a disease or whatever it might be, okay? People have incredible stories, but in a world of, billions of people, you're going to have things happen that may or may not be directly tied to what they believe is the reason behind it, okay? So, if I don't know. So if you have enough people with a certain disease, some of them are just going to get better on their own, okay? And of those people who are going to get better on their own, some of them might try doing some unusual thing, and just because they've done that unusual thing and they happen to get better doesn't necessarily mean that this unusual thing is the reason why they got better, okay? And so, and anecdotes can be very powerful. We hear the, customer testimonials and things like that. They're very powerful and they're very convincing, but they are not necessarily proof that that something works, okay? At the same time, I don't want to say that anecdotal evidence is completely useless. It's just, as far as we're talking from a statistical perspective, we cannot use anecdotal data to justify any kinds of conclusions that we might make, okay? So statistical data come from observational studies and controlled experiments, and we have very specific rules on how this data is gathered, okay? So we can trust that data much more than anecdotes. Okay, so observational studies. Observational studies, okay, should come from people who, observational studies should be done with people who are representative of the population of interest. Okay. Okay, and thus conclusions that we make from the observational study can be then generalized to the population. Okay, so we can say, you know, we didn't study every single adult in the United States, but we surveyed 1,000 adults, and these 1,000 adults are representative of the general U.S. adult population. You know, therefore, the conclusions we make from these 1,000 can be generalized to the entire population. Yes, question?
Is there a rule that says a certain percentage of the population?
There is no rule that says a certain percentage. There are rules that say you take a bigger sample, you'll get more accurate information. That is true, but there's not a rule that says you need to have a certain percentage. And that's kind of, it feels counterintuitive, but the mathematics behind statistics support that kind of notion, if we've done our selection properly. Yes?
So would it be that if the population of the United States is X amount of Caucasian, X amount of African American, X amount of Asian, then your 1,000 person sample should be representative of that, correct?
Yeah, okay, so all right, so yeah, the question is, you know, if the U.S. population is, you know, this percentage of this ethnicity, this percentage another ethnicity, and this percentage another ethnicity, when you take 1,000 people, are you going to have those same percentages? And the answer is you should have something in the ballpark of those things, okay? Of course, and we're going to talk about sampling methods much later on. And sampling is how we select our sample. There are different schools of thought. Some say just pick people at random, and that will work almost all of the time. Of course, from random selection, it is possible that just because of random selection, we happen to get too many of one ethnicity, or, you know, too many males or too few of this other group, or things like that. That can happen. And so another school of thought says, well, we don't want to leave it up to random chance, so I'm going to not forcefully, but just make sure that my sample that I select is exactly this percentage, this ethnicity, and exactly this percentage, this ethnicity, and things like that. And so that also works, but that also requires you to know ahead of time exactly what percentage of the U.S. is this percentage Caucasian, or whatever it might be. And if the information you have is old or outdated or inaccurate, then the sample that you forced to look this way is not going to be truly representative of the population. So you know, you got different schools of thought, right? Because maybe the question is, what percentage of the U.S. is Caucasian, or something like that? Well, then there's no sense in going and say, well, I want to make sure I get a representative sample by making sure I get 40% Caucasian, or something like that, or, you know, whatever. something. So, you know, who knows? But anyway, the idea is you want your sample to be representative of the population, and it's a tough thing, okay, to do, okay? So one method to get representative samples is via what we call simple random sampling, okay, or SRS, okay, and this means we select individuals at random from the population. We will talk about other sampling methods later on in the class. Yes?
I just wanted to clarify, when you talk about the population, you're talking about the population that we're using to get our results. So like your example with the adults, the color blue, population is the adults in the U.S., right?
Yes.
Not the whole population.
Well, that is, so the population is everybody relevant to answering your question. So if we're saying what percentage of U.S. adults like the color blue, if that's our research question, the population is all U.S. adults, all 200-something million, okay? And of course, generally, whatever population that you're going after, your population is way too big to observe directly, okay? And so statistics says we don't have to go for the entire population. We have questions about the entire population, but we don't have to study every single person in the population. We're going to study a representative sample, and based on this sample, we can make conclusions about everybody, okay? So we will talk about other sampling methods later on. Okay, so let me keep talking about observational studies. Or sorry, let me, I'll go back here. I forget that, okay, so I'll let you guys catch up on the writing here. All right, is this okay? Okay, so with observational studies, okay, we do not interfere with the subjects we study. Okay, so we observe, okay, and that's it. That's why it's an observational study. So the key here is that at the end of our study, we might see an association between different phenomena, okay? Okay. So we might see things like maybe we study eating and drinking habits and diets and patient health and obesity and things like that. Okay, and so let's say we do a study on lots of adults, and what we at the end we notice something. Okay, we see patients who drink diet soda have a much higher incidence of heart attacks. And I think there was a real study that showed this. Okay, so does this mean diet soda is linked to higher heart disease? What's going on here? This is what the study showed. We look at the data. We looked at people who drink diet soda. They had a lot of them have heart attacks. Maybe, who knows? I'm just making up numbers, but let's say 8% of them had heart attacks. Or well, I don't know, that's probably too high. Okay. And then we looked at people who didn't drink diet soda, and only 2% had heart attacks or something like that. Okay, so and this is so maybe there's like a 150% increase in heart attack rate between the group that didn't drink diet soda and the group that did drink diet soda. Okay, so do you feel like diet soda is bad for your heart, or what do we think here? Yeah.
There could be another reason, like it could be like the can or something.
I wouldn't even say that. Okay.
On the surface level, yes. But if you go a little deeper, it's what type of people are drinking diet soda.
Exactly.
People who are overweight that drink diet soda, people who are slim down.
So the question isn't, what's going on? Is it diet soda? Is it the contents of the diet soda? It's just, this was an observational study. Okay, so just think of in your mind who drinks diet soda and who doesn't drink diet soda. Okay. So just let certain stereotypes run wild in your brain here, and just picture the person who's drinking diet soda. Picture the person who says, I will never drink diet soda, okay? And you've got different people, okay? And so in general, what you have is, in general, people who are more susceptible to heart attacks are more likely to drink diet soda than someone who is less susceptible to a heart attack, per se. So if you have a healthy person, someone who's very much into, fitness and eating healthy, that person is less unlikely to drink diet soda to begin with. Okay, probably unlikely to drink soda in the first place. So that person is going to be at low risk for heart attacks and will probably not be drinking the diet soda. People who, like soda, which is probably not the healthiest drink to begin with, and maybe, or people with diabetes or things like that who already who are already at a higher risk for heart disease, maybe have to drink diet soda because it's sugar-free and things like that. So this, we cannot say, because this is the result of the study, diet soda thus leads to higher heart attacks or something, okay? So we cannot conclude that diet soda increases the risk of heart attack. Okay? Even if the data behind all of this shows that this statement is correct, we can't conclude that diet soda increases the risk of heart attack, because all this tells us is that the people who are more likely to drink diet soda are more likely to have heart attacks. That's a very different statement than saying diet soda increases the risk of heart attack, okay? So, on the other hand, it may be true that people who are more likely to drink diet soda are more likely to have a heart attack, okay? And that might be a true statement, okay? But that's a very different statement than saying diet soda increases the risk of heart attack. And the only way, so the key thing about observational studies is that no matter how good your observational study is and no matter how strong your data is, you cannot make a cause and effect conclusion from an observational study, okay? So you can never make a cause and effect conclusion from an observational Okay, does this feel okay? And so, and this is actually what the tobacco industry used to kind of combat the argument that smoking caused lung cancer, okay? They would say, oh, we've done all these studies, and every single study shows that people who smoke are like 10 times more likely to develop lung cancer, okay? And they'd say, well, did you do an experiment or was this an observational study? Well, of course it's an observational study. In an experiment, well, we'll talk about experiments, but observational study, and they'd say, well, yeah, that doesn't say anything, because what we believe is that some people are going to develop lung cancer in their life, and this genetic predisposition to develop lung cancer also causes people to want to start smoking. They're looking for something to soothe their lungs that are already predisposed to develop cancer. And you know, it's a little ridiculous to think of that, but it's also, you cannot argue against it from a statistical perspective. Okay. Experiments, on the other hand, may I flip to the next slide? Okay, so in controlled experiments, are created and controlled by the researcher. Okay, and the researcher assigns conditions, sometimes called treatments, to all participants in the study, or I should say in the experiment. Okay. And ideally, all of the aspects that can have an effect on the outcome is controlled to be identical for everybody. Except for the treatment of interest. Okay, so for example, if we wanted to see, does smoking cause lung cancer? Okay, we would have to think, well, what are the different things that could have an effect on someone developing lung cancer? Okay, and it could be like, what is the outside pollution? You know, what, you know, do they exercise? What do they eat? How much stress do they have in their life? And all of this. Okay, and in an ideal experiment, we could control all of these things so that every single person has the exact same conditions that they're going through. Their lives are all identical, okay? And we only vary one thing. This group of people smoke, this group of people don't smoke. And then they go through life, and then everybody has the same identical perfect life or whatever it is, except for this group doesn't smoke and this group smokes. And at the end of the study, if we see a difference between how many people develop lung cancer in this group and how many people develop lung cancer in this group, we can say, aha, everything was exactly the same except for the fact that this group smoked and this group didn't smoke. Therefore, the difference that we observe in lung cancer rate can be attributed to the fact that this group smoked and this group didn't smoke. Okay? Obviously, we can't do that for, you know, we can't do that for everything, but that's the ideal setup, okay? So ideally, you can control all of these other things except for the one thing that you're interested in, okay? And if you do it right, then you can make a cause and effect conclusion and say the difference we observed at the end, these differences is because this group got this treatment, this group got the other treatment, okay? But there's a lot of ethical and just practical limitations. So we can't do an experiment on smoking because what that requires us is we don't is that we assign people which treatment they get. We would have to say, thank you for volunteering for our experiment, and we flipped a coin. Some of you are going to have to start smoking a pack of cigarettes every single day starting tomorrow, and we're going to see if any of you develop lung cancer. Thanks for participating. And there's you know, obviously ethical problems with that. And you know, we could do that to mice who aren't protected by the rules of ethics, and although, you know, a lot of people oppose that as well. But you know, with humans, we can't just force people to do certain things that we're expecting to have negative outcomes in life. So there are a lot of limitations to experiments. But anyway, so let me just kind of jot all of this down. Okay, so if the results show a difference between groups, the difference can be attributed to the different treatments. Okay. Treatments are assigned by the researchers. They are not chosen by the participants. Okay. And then experiments are not always possible because of ethical or practical reasons. We have tools and techniques to try to make everything identical for everyone. Okay, and so one thing is that we don't want. Not only do we not let the people choose which treatment they're getting, we also don't want people to know which treatment they're getting. Okay. So let's say, we want to know, is a drug, a new experimental drug, effective in fighting a disease? Okay? We don't want patients to know, you get the experimental drug and you get the old-fashioned drug that's been around. Okay? So we don't tell them, or maybe we're just trying something out. So we use placebos. Okay? Placebos are pills that look like they're a real drug, but they contain nothing. Okay, because we don't even want people to know which one they have. Okay, so placebos are used so people do not know which treatment they have. Okay, and this general idea of not knowing the treatment, this is known as blinding. Okay. Okay, and sometimes we choose to blind researchers or people who are making evaluations. So I don't know if you're trying to, maybe you're trying out the drug, but it's something like, is this drug effective at improving skin health or something like that? Okay, we don't, as far as I know, there's no machine that says, you have a skin health score of 83, and you have a skin health score of... We don't have an unobjective machine talking about skin health. So you have to go to an expert, and the expert has to look at your skin and say, oh, your skin health is good or bad or something like that. And because it's being evaluated by a human who is, subject to preconceived notions and stuff, you don't want that person making the evaluations to know whether or not you have the which drug you're using or not. Okay, so we might choose to blind that person as well. And if the patient doesn't know and the person evaluating doesn't know, then that's called double blind, and it's all of this tricky stuff. But it's not that complicated. We're just trying to make everything as identical for everyone as possible. Okay. All right, is that good? Okay. So, do your reading, answer the questions in your homework regarding this stuff. Key difference, controlled experiments, researchers control things, and the difference can be attributed to the different treatments if it's done right. So maybe I'll highlight in red here. So you can make a cause and effect conclusion. So far, so good? Okay, let's talk about summarizing data a little bit. We're gonna just delve into the parts of chapter 2. Okay, so we're gonna talk about. Okay, so let's say I just asked a question, okay? What percentage of this class is male? Okay? So, you know, I'm not actually going to do this, but we can go around and how would I answer this question? What would I have to do? I would have to go every single student and count whether you are male or not, right? Okay, and so my raw data table, what does my raw data table look like? How many columns do I need? What are those 2 columns that you're saying?
One.
Just one, right? I just need your sex, okay? Okay, and then and you would either say male or female. Okay, I mean, we could have like a name column, which is not necessary, but this is just to kind of keep track, or a student number. Okay, we could have like a number, and we can just have like 1 student, 2, 3rd student, 4th student, or things like that. Okay, so on and so forth, and you know, there's like 80 of you. Okay, et cetera, et cetera, et cetera. Okay, so this is so I really only need 1 column here. Okay. And so I can create a summary here, a summary table, and this would be known as a frequency table. And what this will say, okay, and so students will either say I am male or female. And I know life can be more complicated, but we'll just, for simplicity's sake, we'll just say everybody answered either male or female, okay? And so we have what we call the frequency or the count, okay? And so let's say I had 36 and 44 here. Okay, so this is my summary table. Okay, I've just gone through, and so you can imagine, you know, I didn't write all 80 rows, but you can imagine 36 of the rows, people said I'm male, 44 of the rows, people said I'm female. Okay, so what is the answer to my question? What % is male? How would I answer this? I would do 36 divided by 80. I get 0.45, which is equal to 45%, right? Okay, so just a quick question. What kind of data am I summarizing in this table here? Am I summarizing numeric data or categorical data? Okay, yeah, so this is, you have to be careful here, right? So many of you look at numbers and you go, oh, numeric. No. Okay, what is the question being asked? We're asking, are you male or female? This is clearly a categorical question, okay? We are summarizing categorical data with this frequency table, okay? It's data, and so numbers appear, but keep in mind, we are still summarizing. We are summarizing categorical data. This table. Don't be fooled that you see a 36 and a 44. Yes, these are numbers. Yes. That is correct. But what kind of data is it?
Categorical.
Categorical, all right? I mean, I guess the question of whether you are male or female could be turned into a numeric question by saying, you know, how many X chromosomes do you have? And people will say, I have one X chromosome, or I have two X chromosomes. And that would be numeric. And you can say, well, I have one more X chromosome than you. And that's a strange way to declare your sex, but I suppose that could work. But in general, you know, we think of sex as a categorical thing, and something like that. And then you get really complicated things, right? Like somebody might have two more X chromosomes, and you know, you have different congenital anomalies. But in general, this is very much a categorical question, categorical data. Okay, being summarized here. Okay, so summary table. This is one way to summarize categorical data, and we can also create a graphic display of this. Okay. All right, and so the graphic display for categorical data is known as a bar chart, and we would create. You need an axis here that delves off counts, so this may be 10, 20, 30, 40, and then 36. I'm just kind of going right here, and this would be male, and 44. Something like that. And you know, if you wanted to color these with different things, you can, but I won't. Okay. So this is a bar chart. Okay, and so bar charts can be used for categorical data. Bar charts are used to graphically summarize categorical data. We can also use a pie chart, okay? But I don't like pie charts. So, you know, pie charts are a circle that look like this, and they were very popular when PowerPoint was first released, and, you know, much to my dismay. So this is a pie chart. This is a bad one, and most pie charts are bad anyway. So, well, and I'll justify my hatred for pie charts because. So you don't have to draw this, but can I flip to the next slide here? Okay, so if I drew a pie chart and just assume my circle was good, and let's say I drew something like this, okay, and you know it's like what vehicle do you have or something, right? And so we have all of these things, and someone says, I drive a Honda, and I have a Ford, and or whatever, and Toyota, and whatever, okay? And then I say, okay, well, look at the pie chart and tell me, are there more Fords, or are there more Hondas or Toyotas? And even if this was like, even if I used a computer to do this, no, like our eyes are so terrible at angles. Like we can't look at angles and do this, okay? However, you know, if we have a bar chart, okay, everyone's eyes are like, I can have just a slight bit of difference between 3 bars, okay? And our eyes can pick this up much easier, okay? We can say like, oh, this one's just a teeny bit taller than this one, and this one's a little bit shorter, and things like that. Our eyes are very good at distinguishing height differences. And, you know, this is just something we can do. And so, you know, bar charts are far superior because, you know, and all you get is this thing and you're just like, well, I don't know, okay? So, but anyway, this is pie charts, and I'm sure you guys have seen pie charts, but we don't need to get into that. Okay, so a few notes about bar charts. Okay, so bar charts again are for categorical data. The order of the bars is arbitrary. Okay, so I could have a bar chart that puts female over here and male over here, or we could have a bar chart that puts male over here and female over here. It doesn't matter, okay? I don't know. So you could say patriarchy be darned, and we're going to put females first, or whatever, you know, whatever you want to do. You can rearrange the order however you want. You can do an alphabetical order. It doesn't matter, okay? Just stylistically, we often leave gaps between bars, okay? We usually put gaps between the bars. Okay. And that's what we have there, okay? And then we have, okay, so when we're talking about data, we have this concept of variation. So actually I'm going to flip to the next slide here. Is this okay? Next slide. Okay. So there's this concept of variation. Variation is very important in statistics. It exists for anything that's a variable, okay? So a variable, we see in the word variable and variation kind of this root of things that vary, okay? The idea of things vary. Everybody is different. Not everybody is the same. Things vary from one person to another. And so we have this idea of variation, okay? And so variation is kind of, can we quantify or can we measure quantify or measure how similar our data is or how different our data is. Okay, so if we say something has high variation, so let me just write, so we can say something, a data set has high variation. Okay. A statement like this means the people in that data set, or the individuals in that data set, are very different from one another. Okay? That everyone you know, looks different, and they're different ages, and they're different whatever. You got lots of variation there, okay? People are people in this data set are very different from one another. Okay, and we can be talking about a numeric variable or a categorical variable. Okay, so we could be talking about a categorical variable like race. Okay, and then you've got all sorts of different races in your data set. Or it could be a numeric variable like age, and then you got young people and old people and everybody, all sorts of different things. Okay, so it could variation can apply to numeric or categorical variables. Okay, so numeric, so for example, age, or categorical example, race. Okay. On the flip side, you can have a data set has little variation. Okay, and so that means the people in your data set are very similar to one another. Okay. Okay, does that make sense? This concept of variation? Yeah, I'll let you guys finish writing that. Okay, so and we'll talk about what this looks like for categorical variables in a chart or something like that. Okay, and so right now we're just kind of leaving this with vague terms like high variation and low variation, and I think that's okay to get started with. Next week when we talk about numeric variables, we'll quantify it with certain summary statistics here. But for categorical variables, we'll just talk about high variation and low variation. But the idea is, if something has high variation, everyone's very different from one another. Of course, you're going to have, maybe you can pick out two individuals in a data set that are similar, but in general, if you look at the data set as a whole, they're very different from one another. And if you have a data set with little variation, then in general the data set is quite similar to one another. Okay, is this okay? All right, so let's just test our understanding here. I'm going to draw. Here's a bar chart. Okay, so I'll do for race of two cities. Okay. Okay, so this is city 1. And all right, so this is for race. We'll say it's always, I don't know exactly what races exist. So we have white, we'll say black, and we'll say Asian, and so in the census, Latino, Hispanic are often considered white, but then they have white, non. So we'll say Latino, and then we'll put other and mixed. This is very I don't know. Okay. Well, okay. So anyway, this is city 1, and so we'll say this is about the number of white people, and this many. This is a bar chart, right? Okay, and this is okay. So that's city 1. And then let me just kind of copy this part. For city 2, I'll bring this over here. Okay. And city 2 will look like this. And I don't know. These are just imaginary cities, okay? So don't get mad at me for not properly representing a city's racial diversity. Okay, is this all right? All right, so which city has more racial variation, not diversity, racial variation? City 1 or city 2? Variation. We're talking about variation here, okay?
More variation?
Which one has more variation? City 1? Okay, so some of you say city 2, city 1. So city 1 has more variation, okay? And if I said which city has more racial diversity, what would you also say? City 1 also has more racial diversity, okay? Because in city 1, whoops, something happened here. What's going on? Okay, because in city 1, white people, black people, Asian people, Latino people, and other race people, these are all equally represented, okay? So if you think of that, okay, picture a city where all of these different races are equally represented, you're going to say that has a lot of diversity there, okay? City 2 is where there are, I'm sorry, I don't know what's going on here. Okay, city 2, you have it seems the majority is white, and the minority races are much less represented. And I think we would say there is less diversity in a place like this. And we can imagine, you can imagine going to a city in, say, China, okay? Maybe like rural China. If you go out into the countryside of rural China, you're going to have very few white people, black people, and every single person in rural China is going to be, not every single person, but almost every single person is going to be Asian, and you're going to have very, very few things, a few other races represented, okay? And we would say there's not much racial diversity in rural China, right? So this would be for rural China. So, little variation here, okay? Or no variation if we're looking at that in terms of this categorical variable. So, when it comes to categorical variables, if one category is very dominant over the other categories, dominant just being much more prominent than the other categories, that reduces variation. Okay, so for categorical variables, if one category is very prominent over the other categories, then there is less variation, okay? And this this applies to any categorical variable, right? So if you think of, is there a lot of variation in the I don't know, and as far as genders go on a submarine? No, because everybody on a submarine is a guy. Okay. Well, I don't know. As far as I've last heard, but is that changing?
Not anymore, yeah, changed.
Oh, it's been changed.
Yeah, because a few weeks ago they said every job in the military will be open to women.
Oh, okay. So,
No,
all
but
right.
there's plenty of females who've always worked on ships.
Well, on ships, yeah, but submarines, like they've had like
Subs.
on a sub, it's like the space is so precious. They were like, we don't want to make a room for women, or something.
That's not the reason.
Huh?
That wasn't the reason.
That wasn't the reason.
No.
All right. Okay. Well, we don't need to get into this discussion, but all right. Well, in general, you're not going to have a lot of women on U.S. submarines. Maybe that will change. Okay. Who knows? All right. But so if we looked at the bar chart for the submarine, you just have one bar for males. Okay, so in our last bit of class, let me just talk about another type of summary table, and this is called a two-way frequency table. Okay, and this is still for categorical variables. And the key here is that we are looking at two categorical variables. Okay, and so it could be something like maybe we looked at the at some city, and we asked, are you male or are you female? And politically, are you registered Democrat, Republican, or neither? Okay. And then, you know, I don't know what the city looks like, but maybe 52 males said I'm Democrat, and 63 said I'm Republican, and 71 said I am neither. Okay, and then as for the females go, maybe 65 and 42 and 58. Okay, I'm just making up numbers here. Okay, and so we could ask questions like, what percent of the city or of the town is male? And how would we answer this? Okay, we would have totals here, and we would have to do 52 plus 71 plus 63. We would have 186 here, and then over here we would have 65 plus 42 plus 58. And we get 165. And here I have 186 plus 165. 351. And so what percentage of the town is male? We would say 186 divided by 351. And we get 0.5299. 52.99%. Or 53%. Okay? Is that okay? We could ask, what percent of males are Democrats? And what is our answer there? 52 divided by 186. Okay, let me whatever number that turns out to be. Okay. What if I ask what percent of Democrats are male? Yeah, so we'd have to add these two together first. Okay, 52 plus 65 adds up to 117. And then we would do 52 divided by 117. Is the distinction between these two questions clear? Okay, and that is different still from this question over here, which I'm going to write. What percent of the town are male Democrats? And what is the answer there? $52 divided by 351. Okay? So the distinction here is we're asking what percentage, and then we've got of males, of Democrats, of the town. Okay? So the group that is of, or whatever, that goes in our denominator, right? So in our denominator, how many males total are there? There's 186, okay? The numerator in all of these cases is 52. These are the number of Democratic males. 52 divided by 186. Over here it's 52 out of 117, and over here it's 52 out of 351. The questions all sound similar, but they are distinct, okay? And if you're not careful, you could be convinced or tricked into believing a certain numbers are larger or smaller, because these all sound very similar, and so the answers are quite different, and so the results, I guess just be careful and make sure you understand the difference between these questions here. Okay, is this all right? Okay, we'll end our lecture today here. I'm looking forward to a great quarter with you guys. You have homework posted online. I'll get these videos and notes posted online as well. And make sure you check out the practice quiz that's posted. We'll see you guys next week. The quiz will start at the beginning of class, so make sure you arrive here on time. Okay, we'll see you guys. Have a good week.